In the last video, we took a look at conservation of momentum for inelastic collisions. We'll hold off on elastic collisions for a bit longer yet in one dimension. And here I'd like to extend that to 2 dimensions. So it's still the same principle that applies. If you've got a system that you can isolate, then you can go ahead and demand that the total momentum of the system be the same before and afterwards. So just to start with a quick example of that, let's say you've just got like a dish or something. Like, have you ever had a dish that you got super hot out of the microwave? You set it down on the wet spot of the counter accidentally and it broke into pieces flying. Well, it happened to me once anyway. Fortunately, I realized what was going on and I ducked down under the counter while the pieces flew over me. Anyway, let's say that this, hopefully this unfortunate incident will never happen to you, but let's just say it happened. So let's say it broke into 3 pieces. And just to make things simple, let's say they're all of equal mass. And the one piece flies straight to the north at 10 meters per second. One of the pieces flies straight east at 10 meters per second. Let's try to figure out the magnitude and the direction of the speed, of the velocity of the third piece. So when I conserve momentum in one dimension, you remember I said that I like handling the variables like we were back when we were doing kinematics, where we let the plus and minus signs do their thing when we substitute the numbers in. In 2 dimensions, I find it better to treat the vectors like we've been treating force vectors, where it's better to handle the plus and minus signs and the angles and everything before we stick values in. So let's just go through an example of that. So first off, can I make this system isolated? Sure. The plate is sitting on the counter, so there's gravity pulling it into the counter, normal force pushing it up off the counter, and those cancel. And that was it for forces. So yeah, there's no force acting on the plate. And if I make my system the 3 plate shards flying off, it'll still only have you'll still have no net force acting on it. So with that, we can go ahead and say that the total momentum final is equal to the total momentum initial. But now here we need to actually go ahead and take x and y components of this. So let's go take a look at my x component. And we can start by asking ourselves, all right, do we have any shards that are flying either totally or partially in x? Well, v1 doesn't count, it's moving purely in y. v2 is moving in x, and its momentum would be mv2. Remember, we're saying that the shards are all equal mass. And it's directed entirely along x, so I don't need to take any components. Then anything that's acting left-ish, well, v3 is moving to the left-ish. So I'll put in a minus sign to handle the fact that we're going to the left. And then its momentum would be mv3, but I need to take the component of this. And so this is going to be cosine theta. All right, and what was the x component of momentum initially? Well, the plate was at rest, so 0. Okay. And let's go ahead and do the same thing in the y direction. So piece number 1 is flying straight up, so it's MV1 flying straight up, and then this piece is flying straight, has a downward component, so the total momentum would be MV3, but we want this piece of it right here, which is going to give me a sine theta, and that will equal 0. All right. So our unknowns are V3 and theta. We never knew what the mass of the plate was, but the fact that they were equal shards meant that all the pieces were m, and thankfully when I divide through by m on the left, I'll just have 0 divided by m on the right, which is 0. Same there. Okay, so that helps a bit. So this relation will tell me that V3 sine theta equals V1. This will tell me that V3 cosine theta equals V2. So is there a way that I can isolate at least something? The answer is yeah. If I were to take the y equation divided by the x, I would cancel V3 and leave me with a tangent of theta, so let's go and do that. So V3 sine theta equals V1, and I'll divide the left-hand side by V3 cosine theta. We'll divide the right-hand side by what that's equal to, V2, cancel, cancel. Sine over cosine is tangent. So the tangent of theta is V1, sorry about that, V1 over V2. So then to get theta all by itself, we'll have to take the arctangent of both sides. So theta will be the arctangent of V1 over V2. And before we go any further, we should just ask ourselves, do the units make sense? Well, the numerator inside the arctangent is meters per second. The denominator inside the arctangent is meters per second. All of that will cancel to leave us something without units, which is what you need if you are stuck inside an inverse trigonometric function. Okay, so we said the pieces 1 and 2 were both flying off at 10 meters per second. So this will be the arctangent of 10 meters per second over 10 meters per second. Arctangent. Cancel, cancel. In fact, it's the arctangent of 1, which turns out to be 45 degrees. Okay, now that we got the direction sorted, we can use either the x or the y equation to get the magnitude of V3. So let's use the y equation. So we have V3 sine theta equals V1. So V3 will equal V1 over sine theta over sine theta. So this will be 10 meters per second over the sine of 45 degrees. Will give us 14 meters per second. So to recap here, we verified that our system was isolated. Since it was isolated, we demanded that the total momentum final equal the total momentum initial. This is a vector relation, so we took x and y components. In 2D, we handle, or at least I handle, my signs explicitly because I find that to be less confusing. So I handle my direction signs the way we do for forces rather than the way we do in kinematics. And then from there, it was doing algebra to get the answers. Alrighty. So with that, let's go ahead and do one more example, and then we'll call it a video. So in this example here, let's say that we're on a sheet of ice just to make friction go away, and I have a 1 kilogram puck. I know hockey pucks are less massive than that, and this is less massive than a curling stone, so something in between those. I'm sure there's a sport somewhere where that's the right size. And let's say it slides into a 2 kilogram puck. That's initially at rest. So here we'll say that V1 initial is 5 meters per second. Now after the collision, we know that my M1 puck is going to go flying off. And although I don't know the final speed, somebody measured that it flew off at 30 degrees. And so we would like to know the final speed of it. Similarly, my puck that was at rest, we don't know its final speed, but somebody helpfully measured that the angle it scattered off at was 40 degrees. All right, so here when you're choosing a coordinate system, it will make sense to align the x-axis along V1 initial. And this is because since object 2 isn't moving to begin with, if I align things along V1 initial, that means only the x equation will involve V1 initial. The y equation won't, and that will make the algebra easier. So let's go ahead and do it. So again, same deal. You have normal force trying to push both of the objects off the ice sheet, and gravity trying to pull them into the ice sheet, but that cancels out, so the net external force is 0 because we made sure it was ice so that there wouldn't be any friction. And that means that we can treat the pair of pucks as an isolated system. So that will allow us to demand that P total final equal P total initial. And again, this is now a vector equation, so we have to separate this out in the land of x and the land of y. So in the land of x, what pieces do we have? Well, we have piece number 1 flying off. Its total momentum would be m1 v1 final, but we only want the x component of it, so that'll be cosine theta 1 final. Similarly, we also have, finally, piece 2 flying off. Its total momentum would be m2 v2 final, but we only want the x component of it, so that will be cosine theta 2 final. And this will equal the x component momentum initially. Well, we set our coordinate system so that m1 was moving entirely along x, so this will just be m1 v1 initial. All right, now we need to go to the land of y and set up a similar relation. So if we look at P total final here, well, the only thing we've got going vertically is piece 1. It has the total momentum would be m1 v1 final, but the vertical piece will be times sine theta 1 final. Now piece 2 is heading in a generally down-ish direction, so we need to put in a minus sign in order to account for the fact that it's going down. And the total momentum would be m2 v2 final, but again we need to take just the y piece of that, so it'll be sine theta 2 final equals, well, since we chose our coordinate system so that the object was moving initially purely along x, there's nothing along y, and so that's equal to 0. Now we see the value of making that choice of coordinate system. This will give us a nice clean relationship between v1 final and v2 final that we can then substitute into the other equation, which will be less clean. But at least this will make the algebra a little less gacky. So the physics is all set up, and now we just need to do a little bit of math for a while to crank out the answer. The two unknowns in this problem are V1 final and V2 final, and thankfully we have two equations for them. So we will go ahead and solve the equations in two unknowns. My strategy here is I'm going to take the y equation, formally solve that for V2 final in terms of V1 final, take that solution and substitute into the x equation so I can then relate V1 final to V1 initial. So with the strategy mapped out, let's implement it. All right, so I want to get V2 final all by itself. So first thing I want to do would be to add this to both sides. So M2 V2 final sine theta 2 final equals M1 V1 final sine theta 1 final, and then divide through by the M2 and the sine theta 2 final. So V2 final equals M1 over M2 V1 final sine theta 1 final over sine theta 2 final. Awesome. So now our strategy is going to call for taking that formal solution of V2 final in terms of V1 final and sticking that in right here into the other equation. So let's go ahead and do that. So the first term gets to just sit all by itself. That will be M1 V1 final cosine theta 1 final plus M2. Now you get to put in what V2 final is. So that'll be times M1 over M2 V1 final sine theta 1 final over sine theta 2 final. And then we still have that cosine theta 2 final over there equals M1 V1 initial. Well, that seems awful, and it's certainly not pretty. But you'll notice that both terms have a V1 on the left, V1 final, and on the right we just have our, let me clean that up a little bit, we just have a V1 initial. Okay, and the small favors don't stop there. Look here, the M2's cancel. Now every term has an M1, so I can divide the entire equation through by M1, making those go away. And then I can group out a V1 final from the remaining terms. So V1 final times cosine theta 1 final plus sine theta 1 final. And here you can clean things, make things a little prettier by realizing that cosine theta 2 final divided by sine theta 2 final is cotangent theta 2 final. And that equals V1 initial. Sorry. All right, so all that's left is just to divide by everything in the parentheses. So V1 final equals V1 initial over cosine theta 1 final plus sine theta 1 final cotangent theta 2 final. And if you want, you can play around to make this look just a little more symmetric or whatever, but I don't feel a burning need to. I think we're good at this point. So let's go and put in our values. V1 initial is 5 meters per second. For theta 1 final, that was 30 degrees, so cosine 30 degrees plus the sine of 30 degrees cotangent of 40 degrees. Grind that out through your calculator, you'll get 3.42 meters per second. All right, now that we have that, we can go back and use this, we can go back and use this guy right here to give me my relationship for V2. So let's just do a quick copy paste. Copy, paste, clean that up just a bit. There we go. So putting in now, M1 is 1 kilogram, M2 is 2 kilograms. My V1 final is 3.42 meters per second, or sine 30 over sine 40, and that will give us 1.33 meters per second. No, both of those numbers are less than 5 meters per second, so the answer seems plausible, and we're good. Alrighty, so I'll see you in the next series of videos. Catch you later in cyberspace.